Hi! In this video, we'll be going through the series solution near a regular singular point for a general second order linear equation. So, as the name suggests, we want to find a series solution near the regular singular point. So let's say x equals to 0 is the point that we want to check whether it's a singular point and is regular. So to check that it's singular, you just need to show that px equals to 0. And then to show that it's regular, you just need to show that x squared rx over px is finite, the limit, and x qx over px is also finite, as what we have done earlier in the Euler's equation case. But now we have a general one, so after showing that it is a regular singular point, we must convert this second order into the Euler equation form, and then so after reducing it to the Euler's equation form, it should look something like this. And with that, we would suppose that the solution would equals to something like the Euler one, which is x to the power n, or x to the power, we sub in x to the power n to try. But in this case now, our series solution an xn will be like shifted a bit, and later we'll see why. So xn, we just shift it by a value r plus n. Then we solve for the equation, and we need to find the values of r so that the coefficients are non-zero. So this is known as the method of Frobenius, and we will see how we solve it with this differential equation. So this is the differential equation, and it's easy to check that x equals to 0 is a regular singular point. And so we assume that there is a solution of the form an x to the power r plus n. Then we differentiate once and twice to get these expressions and substitute back into equation number 9. With that now, we are able to compare coefficients and see that an times this expression xr plus this whole series equals to 0, meaning this portion over here must equals to 0. But an cannot be 0, so you only get this part to be 0, and this is known as the integral equation. So solving it, we find that r equals to 1 and r2, there will be two solutions. So now, when we have two solutions, what will happen is we will test out one first, and then we'll solve to get this recurrence relation, and we see whether this recurrence relation is solvable. If it is, then this becomes, we can write the an to be one of these coefficients, and then we substitute it back in to get one solution, one solution from for the fundamental set. So we got the y1 to equals to this value, and we see that it converges, so it is a valid solution. And now we just use the other route to get the other solution, and we do the same steps, check that it works, and then we say that these two solutions now form the fundamental set of solutions. So a general solution will be just a linear combination of this and this, which is still a series solution. So this example highlights how we use what we have learned earlier in the Euler case, where it's an xn. Now we just an xn plus r, and we find r using the integral equation. So the justification for the Frobenius method, well, it is a bit more complicated, but in short, it will definitely exist as long as the two distinct roots, as long as the roots are distinct and they don't differ by an integer. In the textbook you read, you can actually find solutions for equal roots and what happens when they differ by an integer. But for this video, we'll keep it short and simple, and we won't go through those parts. So we will just give a brief explanation on why we use what we did. So regular singular point means these limits exist, and because they exist and are finite, we then can assume that these are analytic and can be expanded in the following series. So if you see this is like your one part and this the other, and we just take the, we assume the series of this form, we just try it out and we get this. If we collect all the coefficients and set it to be 0, then it must equal to this, and this is the integral equation. So then how about for the x n plus r portion, the more complicated part, which is like this part? Then we can expand out and see this following, and we isolate the terms together. So we see that an and this portion must equals to the terms involving a0 to an minus 1 and p0 to pn and q0 to qn. And then this part is just the integral equation plus a constant. So as long as this integral equation does not equal to 0, then you can actually solve for an. Because if this part is non-zero, then this part will get some value, and then you just an is just that value in terms of all the predecessor terms that you have defined. So it will be possible to do it. And so actually the coefficient will then only determine on these 3 factors. So most importantly from this video is you understand how to use the method for beginners now to actually solve for general regular singular points solutions. That's all for this video. I hope you have enjoyed it, and I'll catch you in the next one. Bye!